Hello, my name is James Mullinix. I'm a PhD student with the Computational Science Research Center at SDSU. My advisor is Anthony Luque. Today, I'm going to discuss the interpretation of power law model parameters from fitting. And the reason I'm picking this is that it is an element of the research that I'm doing on fractals. I'm going to present this in a little bit more generic way so that you can apply it to general power law models. But my concrete example will be fractals. So without further ado, the model that we're going to study follows this pattern, y equals ax to the r. And the typical protocol for analyzing these types of models is to linearize the system and then perform a linear regression. And as you'll note, the slope in the linearized model is that you would get from a linear regression is the growth rate parameter, r. So we'll get right into the specialization that we're doing. What we're going to do is pick a point in the set of points, say x naught, y naught, and we're going to a-dimensionalize the x points by dividing by x naught, and a-dimensionalize the y points by dividing by y naught. And we'll also go ahead and a-dimensionalize the prefactor. And what we find is that using this technique, we should have a prefactor of 1. Now, it's important to note that most people who perform power law analysis outside of allometry or allometric modeling tend to sort of discard that prefactor. Well, it turns out it can be rather useful. And I'll give an example here, our concrete examples with box counting. The way the box counting works is we have a set, which is a collection of points, and we want to analyze the geometry some kind of way. In fact, we want to understand what dimension it occupies. And so what we'll do is we will cover the set in boxes and count how many boxes it takes of a particular size. So in this case, the size of the boxes is our x, which we're calling delta, and the number of boxes that it takes to cover the set is what's going to be our y. And we'll call that n in this new model. And the growth rate parameter is minus d, is the opposite sign of the dimension. And so the a-dimensionalization we'll take is to choose the minimum axis aligned bounding box. It basically it's the smallest box that could completely cover the set. And that yields the n naught, the first point that calculates the number of boxes, is just going to be 1, because only 1 box is required to cover the whole set. And delta naught is delta naught, whatever that measure is, it doesn't really matter. So we're going to perform this recursively, and then log transform and get our slope. It turns out that Sierpinski's triangle, which is the object we're investigating, has a known dimension of 1.585. And when we perform our regression and look at the 95% confidence interval, indeed 1.585 is in that range. So everything looks hunky-dory, except that our prefactor, our intercept in a linear model, is does not contain 1. The confidence interval does not contain 1, and that is problematic. So that tells us that something funky is going on, either in our technique, our modeling, or the underlying data doesn't match the method we use. So let's just take a quick look at what we do. So here's exactly how we apply this algorithm. We bisect, and then we count the number of boxes. Now, this is one way of doing box counting. There's lots of ways to do it. This is just a really common, popular, general method for doing it. And so what we see from this is that if we rewind to this stage, the first step, the first iteration, what we find is of bisecting is that there are 4 boxes here used to cover the set, but really, if we smartly place the boxes, we would only need 3. Okay, and as we continue down the path, we see this happening at every step. There is 1 extra box per little unit at every step, at every stage. So what that corresponds to is we are actually using 4 boxes when we should be using 3, which is 4/3, 1.33333. And that is within the confidence interval. So it turns out that parameter, if we a-dimensionalize it, can tell us something about the method that we're using to generate the n values and the deltas, right? Was the method we chose a good method? And it appears that even though it gave us the right slope, that it was kind of biased in some way. So maybe we shouldn't use this method for generating this. Now, in the general case, we won't necessarily know exactly what the right slope is, but we can tell right away if the intercept isn't 1, that something is happening. And that's a really important piece of information. Well, that's about it. So thank you very much for your time. And I hope that this has been interesting and illuminating and useful to you.